Hello, this is Sriram, and today we're going to be reviewing chapter 5.6. In calculus is called related rates. So what are related rates? So a related rates problem is basically um, a problem where we know the rate of something and we want to use that rate to find the rate of something else. Hence the word related here. So we want to relate one rate to the other. So hopefully by the end of the video, I can walk you some examples and you might have a firmer understanding of how to solve related rate problems. They're basically a lot of word problems you'll see, and this will definitely be on the AP exam on many of Mr. Pinger's tests, so it's a really important topic to know. So let's start with a simple problem here. So it's a common ladder problem. So we have a ladder here and it's basically one part of it is on the ground, the other is on the a wall here. So we're given that the ladder is 10 feet long, okay, and it's resting up. Initially, it'll rest all the way up, like flat, but then we start moving the bottom away. So we start from wall and start moving it away, and we know that we are pulling the bottom away at 3 feet per second. We want to find how fast is the top of the ladder moving um, when the bottom of the ladder is 6 feet. So this is a 6 feet case, right? So to tackle this problem, it's important to write down what you already know. We know that the length is 10 feet. This is the ladder. We also know that the bottom is moving. Let's call this x. Let's call the height h. Okay. We also know that the change in x, this is basically rate. So when you see the word rate, you should think of, obviously per second, you should think of how fast x is changing. And we already know the notation for it. dx over dt, remember? And it's equal to 3 feet per second. Alright, so we also know that x is equal to 6. What we want to find though is dh by dt when x is 6. So one might notice that this is actually a right triangle. Let me draw it again. So we already know a famous theorem that can relate this length, and the hypotenuse together. Well, we learned this since geometry, right? It's basically h squared plus h squared equals 100. Now, let's actually write all of these as functions of time, so it'll be a bit easier to process. So this is actually just going to be h of t. H of t basically means the height at the given time. So h of t squared plus x of t squared. And what is that equal to? Well, a squared plus b squared is equal to c squared. 10 squared is just 100, right? We also know that at time t, x is equal to 6. The x of t just means the value of x at time t. Since x is equal to 6, we can substitute a 36 over here, and we all know that 100 minus 36 is 64, and then the square root of 64 is just 8. So h at time t is equal to 8 because h squared is 64. So h will be 8. Great. We're one step closer. Right. So now we actually notice that this is a 6, 8, 10 triangle. But we know h, but we want to find the change in h. Right? Hmm. Well, we learned something called implicit deriving, right? We have h of t squared plus x of t squared equals 100. Hmm. We want to really take the derivative of this maybe, and then maybe we could get a h prime of t term, right? How about we look into that a bit more? So we have h squared. If I just use it not to cause confusion, I'll just put a bracket around and add the exponent. X of t squared equals 100. Now, what if we were going to implicit derive based on t, right? So this is just going to be 2 times h of t times h prime of t. This is basically the chain rule. Plus 2x of t times x prime of t. And then since 100 is just a constant here, you can just make this 0. No problems there. What's nice to know is that we already know most of this. In fact, we know h of t, we know x of t, we also know x prime of t, right? So always try to find a way to derive stuff. Find a way to implicit derive like this. We're basically implicitly deriving based on t. And once again, we move the 2 down to h of t. But remember, we are using the chain rule here. So we have to differentiate h of t as well. So we had to add the h prime of t. Same thing goes with this because we are deriving with respect to time. Now, h of t, we already said was going to be 8. H prime of t, we still do not know that. However, we know x of t, 6, and then the rate of x, which is 3. So now we can just write 2 times 8 times h prime of t plus 2 times 6 times 3 equals 0. Great. Now it's just basic algebra here, right? We just want to find h prime of t. So 16 h prime of t is plus 36 equals 0. Move the 36 to the other side, we'll get 16 h prime of t equals negative 36. We can just divide by 16 now. So h prime of t is equal to negative 9 over 4. Now, one thing the AP exam really likes to do is make sure you actually know what this means. Let me make the apostrophe a bit better here. So this is the change. So as I was saying, the AP wants to make sure you're not just writing down a random number and going away. Sometimes they might ask you, what does this actually mean? Well, we are calculus students. We know that this is a rate. And we also know that dx over dt from the other slide was in feet per second. Because this is basically the change in elevation per second. So unit is still going to be feet per second. What if you had to write this as a sentence? Well, the best way to say it is, um, so h of t is the change in height at time t, sorry, and is equal to, there's more ways to say this. Like for example, you could say h of t, the height of the ladder is just decreasing at 9 over 4, which is 2.25 feet per second at time t, right? Or you can write when x is equal to, when the length, well, the ground length of the ladder is 6, the height is decreasing by negative 2 by 2.25 feet per second. There are many ways you can write this. Goal is to make the AP test wants to make sure you actually know what you found, what that means. They want to make sure you know that you're just not writing down a random number. All right, let's do another one. Let's open the new slide. So let's see. Guess we can do something in 3D now. So a cone. So we have a little cone here. A cone is being filled with water. It's blue. Okay, and it's filled at a constant rate of 2.5 feet cubed per minute. So the fact that this is in feet cubed by minute tells me that this is change in volume. Because remember, just one-dimensional length has just feet, that's it. But if we have like a square, you'll say the area is in feet squared. Volume, use feet cubed. So that's a good thing to know. We also know that a cone has an overall radius of 2 feet. And we also were given that the height is 3 feet. So now there are two small problems. how fast is the volume rising, the rate in the water level, when the height of the water is 1.2 feet high? Let me rephrase that. So how fast is basically the height changing when the height is at 1.2 feet high? Okay, so that's our first question. So what do we know right now? Well, for starters, we know that the volume of a cone is just going to be 1 by 3 pi r squared times height. It's a given. Now, we also need to find something else. Maybe we could find another equation that could help us. Because we could take the derivative of this, and then it can help us. But we want something that relates R and H, right? Well, think about this. So if we take a small cross section, just the right half of it, we can see that the cone is basically a cross section in the middle. You could basically see the cone can be of a 2 by 3 right triangle. And in all the water, let's say that there's some water in the cone already. Notice how both of them are similar. They have the same angle here, and they're the right, and both of them have right angles. So by the angle similarity, both these right triangles are similar. So what does that mean? Well, if this is the current radius, so let's say the current radius of the water is r and the current height of the water is h. We know from geometry that r over h is equal to 2 over 3. In other words, r is equal to 2 over 3 times height. Now, what we can do is simplify this into just two variables, v and h, right? So to do this, it's basically going to be a simple substitution. So this is going to be, well, v equals 1 by 3 pi 2 over 3 h squared times height. And to save you time, this is just going to be 4 pi by 27. 4 pi by 27 h cubed. And we can also do h of t as well. So what else do we know here? We are actually given the change in volume. So I'm going to move on to another slide now that we basically got our main formula. Okay, so V is equal to 4 pi over 27 h of t. I can just do h of t cubed for now. It's the same thing though, right? So what can we do now? We already know the change in volume. dV, change in volume over time. Change in volume over time is equal to 2/5 feet cubed a minute. We were given this at the start of the problem. Great. So now what do we actually want to find? We want to find dH by dt, how fast the water level is rising. It's easy to confuse this as how fast the volume is rising, but water level is basically how high does the water get over time. So it says change in height. All right. And we want to find this when H equals 1.2. Okay. So now we can just take the derivative of this and set it equal to 2.5, because the derivative of this equation must be equal to 2.5 for this problem to make any sense at all. Great. So let's take the derivative of this. Luckily, we know calculus and we already have went through played with derivatives for a long time. So we know that we can just use the power rule here and then followed by the chain rule. So dv by dt is also equal to, well, move the 3 to get 12 pi over 27, and you'll get h squared of t times h prime. We're taking its respect to time, and this is a composed function. And we can also use notation like dh by dt, anything that flows your boat, anything that you're used to. Okay, so now we can just plug in stuff again. We know that this is equal to 2.5. We know that h of t is equal to 1.2, and then we want to find dH by dt. So now the problem is pretty solvable because of all these decimals. I'm not going to go through all the computation, but if we want to try it, the answer is just going to be dH by dt equals 1.243 feet per minute. Then once again, we're talking about height here. We're seeing how high the water level reaches. So it's just going to be in feet per minute. So I'd suggest you can just check yourself on the math right now. Take a pause this video, look at that, just to confirm everything, and try doing some active math. All right. So now that hopefully you tried this on your own, we can do part B. So how fast is the exposed surface of the water in the cone changing at the same moment? So let's take a look at the water here. So let's say it's like a small cone here. What's basically saying is that if we have a plastic type of cylinder, the surface, the cone part of the cone, it's weird to say it, but it's basically hidden. The surface, though, what you look down when you drink some water, is exposed. So they want to find you basically want to find the how fast the exposed surface are. Basically, the circle is changing at the same moment. So what is the area of the circle? Simple. If the radius of the water is r, we know the area is equal to pi r squared, right? We also know from the previous problem, dH by dt is equal to 1.243. So we also know how to relate R and H. See where I'm going here? I'm trying to relate the rate of R with something we already know, right? So R is equal to 2 over 3 H. Now what you could do as well is go back to the previous problem and see how fast the radius is changing. But we already found how fast the height is changing. Why not just convert to that and use it instead of spending a lot more time re-deriving stuff, right? So this is equal to pi times 2 over 3 H squared, and this is all equal to 4 pi over 9 H squared. Great. Now we just need to find the derivative of this. Luckily, this is a lot easier than the previous one. So dA by dt is equal to 8 pi over 9 h times dH by dt. Or you can use h prime of t. And then this is equal to 8 pi by 9 times 1.2 times 1.243. Because h at time t is equal to 1.2, right? That's basically it's still how fast is the exposed surface of the water is the cone changing. Is the water in the cone changing when the height is 1.2 feet high, right? So this is basically equal to 4.165 feet squared per minute. And once again, I suggest you can try doing the calculations on your own. It's a good calculator practice, and you can also verify that the answer is actually correct, right? All right. So I think we can do one more problem. So this is another type of common related rates problem, and it's basically about two particles or cars or planes. Generally, like they use any type of vehicle in this problem. So suppose particle A, I'll use a different color, I guess. Yeah. So particle A and just green, particle B. Suppose particle A and B start at the same spot. Let's say they start at origin, but then they start to head east and then head north, right? So let's say A is heading east at, I guess I'll just use the same color. A is heading east at 10 meters per second. And then B is heading north at 5 meters per second. Right. So at what rate is the distance between the particles changing when B is 15 meters away? So what do we want to find? It's basically the length of this purple line over here, the hypotenuse, because A is going to stay confined to the x-axis, B is going to stay confined to the y-axis, and we know that the coordinate grid, this is a right angle, so this is going to be a right triangle. You all might be thinking of the theorem we use, the Pythagorean theorem again, and yeah, that's what we're going to use for this problem. But let's check, see what we know and what we need to find to stay organized. So we know that dA over time is equal to 10, and dB, change in particle A, change in particle B. over time is equal to 5. Now, let's call this um, W. So let's say this is a function of time, basically the hypotenuse at time t. So we want to find dw over dt, change in w at b equals 15. Great. So once again, we can use the Pythagorean theorem again. We know that a squared plus b squared is equal to w squared. A is the distance from the origin, b is the distance from the origin as well. And then w is a hypotenuse. Great. So since this is all based on time, we can just do another implicit derivation and then get the same result again. So we'll get 2 times a of t times a prime of t plus 2 times b of t times b prime of t equals 2 times w of t times w prime of t. And then yeah, you could also use other notation as well. What do we know though? We know what b of t is, and then we also know um, we can also find other variables as well, right? So if b is at 15, so 15 meters from the origin, and it has been traveling at 5 meters per second the whole time, distance is equal to rate times time. The distance is 15, the rate is 5, and then t. T is equal to 3. What does it mean? It's been 3 seconds. So A has been traveling for 3 seconds then. 3 seconds is just going to be, that's just going to mean 30, because 3 rate times 10. I mean, 10 is the rate and 3 is the time, so the distance is going to be 30. So we know A, B, and then we can just find W. For now, I'm just going to leave it in its square root form. So it's just going to be 11,125. Great. So now all we have to do is plug this in. So I'm going to copy all this over, paste it here real quick. Great. So now all we have to do is plug stuff in. 2 times 30, that's A of t, times 10, that's a prime of t, plus 2 times 15, that's b of t, times b prime of t, just going to be 5, right? This is equal to 2 times square root of 1125 times change in w over time. Great. So all we have to do is solve for this. Once again, I guess we could start with the left-hand side. So this is going to be 600 plus 150 equals, unless you could just copy that down, 750 is equal to 2 square root of 1125 times dw of dt, and then you can just plug this in your calculator, and then if you want to check it, the answer is going to be 11.180 meters per second. What does this mean? It means that the distance between A and B is changing at 11.18 meters per second when the position of B is 15 meters from the origin. So obviously it's always important to like write your units down on every test basically. If you were given units like meters per second, make sure it's meters per second. If we were finding area, then it would be meters squared per second. If we are finding the change in volume, it would be meters cubed per second. So always keep that in mind, as units are pretty important. Right. So hopefully these are like the most common types of related rate problems. There are some other variants of it, but these are what you will mainly see on tests. And then sometimes you'll also get stuff like you have to use trigonometry. For example, you want to find the change in this angle. It's simply the same thing though. You just need to find an equation that relates the angle to these side lengths, for example. So you want to find how fast is the angle changing when blah blah blah. Well, you can do something like sine theta is equal to opposite by hypotenuse, and you can just derive it, and you can go on to doing the finding your rate. So that's basically the process of this. You can what's important to do is in all problems, if you given a diagram, make sure to draw that. So that's your first step. Then you're gonna think about what you already have. So if they give you like b is at 15, or like the change in a and change in b, write it down, and then you can go on to find models. So you know how the Pythagorean theorems work, right? If you think you can use a Pythagorean theorem, then write it down. Say that a squared plus b squared equals c squared. Then find if we can relate any more variables. The more equations you have, the better. And then finally find something to substitute, and then you can implicit derive and then plug in what you already know, and you can separate the rate, and there you go. So related rate problems, this is basically the general way of doing them. Obviously there are a lot of different variants of this, so there's no like instant formula or solution for this. It's basically the rate I'm given, rate I wish to find, equation relating the quantities, and then you basically use some sort of derivation method, now which could be implicit or general deriving stuff. So yeah, that's basically the gist of it. Yeah, thank you.